Gravity. It's a force we can't see, but we feel it every day. It's the reason we stick to the Earth and why things fall down instead of up. In simple terms, gravity is a pulling force between any two objects that have mass. The more massive an object, the stronger its gravitational pull. Imagine holding a tennis ball and a bowling ball. Naturally, the bowling ball feels heavier. This is because it has more mass and therefore a stronger gravitational pull towards the Earth. But don't be fooled. Even the tiny tennis ball exerts its own gravitational pull, albeit much weaker. Gravity isn't just about objects falling to the ground. It's a fundamental force that governs the motion of planets, stars, and even galaxies across the vast expanse of the universe. It's the invisible hand that shapes the cosmos, pulling matter together and creating the structures we observe. Our understanding of gravity began with Sir Isaac Newton, a brilliant scientist who lived in the 17th century. Legend has it that Newton had an epiphany when an apple fell from a tree, prompting him to ponder the force that brought it crashing down. This simple observation led him to formulate his law of universal gravitation. Newton's law states that every object in the universe attracts every other object with a force that is directly proportional to their masses, and inversely proportional to the square of the distance between their centers. In simpler terms, the heavier the objects and the closer they are, the stronger the gravitational attraction between them. Newton's law was a groundbreaking discovery, explaining why the moon orbits the Earth and why the Earth orbits the sun. It provided a framework for understanding the movements of celestial bodies, revolutionizing our understanding of the cosmos. While Newton's law provided a remarkably accurate description of gravity, it wasn't the whole story. In the early 20th century, Albert Einstein, a scientific revolutionary, proposed a radical new theory that would forever change our understanding of gravity, the general theory of relativity. Einstein's genius was to realize that gravity is not a force acting at a distance as Newton had proposed, but rather a consequence of the curvature of space and time. Imagine a bowling ball placed on a trampoline. The ball creates a dip in the fabric, and if you roll a marble nearby, it will curve towards the bowling ball, drawn by the indentation. Similarly, massive objects like stars and planets warp the fabric of space-time around them. This curvature is what we experience as gravity. Objects don't simply fall towards each other, they follow the curves in space-time created by the presence of mass and energy. Section 4. Cosmic Dancers, From Our Sun to Black Holes. The Sun, the star at the center of our solar system, is a powerful example of gravity in action. Its immense mass creates a gravitational well that keeps all the planets, including Earth, in orbit around it. Just like a ball swirling around a roulette wheel, the planets are constantly being pulled towards the Sun, but their own motion prevents them from falling in. Black holes, on the other hand, represent gravity at its most extreme. These enigmatic objects are so incredibly dense that nothing, not even light, can escape their gravitational pull once it crosses a certain boundary, known as the event horizon. Imagine the entire mass of the Sun squeezed into a sphere just a few miles across. That's the kind of density we're talking about with black holes. They are cosmic vacuum cleaners, relentlessly devouring anything that ventures too close. Section 5. Earthly Ties, Gravity's Impact on Our World. Here on Earth, gravity is the unseen force that shapes our everyday lives. It keeps our feet firmly planted on the ground, dictates the flow of rivers, and even influences the rhythm of the tides. Without gravity, our world would be a very different place. Think about the simple act of throwing a ball. Gravity is what pulls the ball back down to Earth after it leaves your hand, giving it its parabolic trajectory. It's also what keeps our atmosphere from drifting off into space, allowing us to breathe and experience weather patterns. Gravity is also essential for life itself. It plays a crucial role in the formation of stars and planets, creating the conditions necessary for life to emerge. On Earth, gravity influences the development of organisms, determining everything from the shape of trees to the structure of our bones. While we have a good understanding of gravity on large scales, there are still mysteries to be unraveled, particularly at the quantum level. Scientists are working tirelessly to understand how gravity behaves at the smallest scales, where the laws of quantum mechanics come into play. This quest for a unified theory of quantum gravity is one of the biggest challenges in modern physics.